We barely even think about it anymore. Raw materials enter a line, and a few minutes later, finished products emerge with absolute precision. When you observe an entire assembly line, you are watching thousands of independent pneumatic arms, conveyor belts, and welding torches operating in exact orchestrated harmony. That orchestration requires a centralized brain. Tucked away inside the heavy steel control cabinets of these facilities is an industrial computer known as a programmable logic controller, or PLC. The PLC operates as the factory's nervous system. It constantly reads the physical environment, checking voltages, pressure sensors, and limit switches, and then decides exactly when to fire a motor or open a valve based on those readings. But a PLC is a blank slate out of the box. It doesn't inherently know how to sort packages or build a car. Humans have to translate their operational goals into a set of instructions the machine can execute. That translation process is PLC programming. It bridges human logic and mechanical action, keeping the entire system running seamlessly. Looking at this reference sheet, you can see there are 5 recognized programming languages, governed by the IEC 61131-3 standard. But the dominant language running the floor is the first one on this list, ladder diagram, commonly called ladder logic. Unlike modern text-based coding languages, it is built vertically with horizontal rungs. It is designed to look exactly like a physical electrical ladder. The entire system relies on 3 core symbols. You have normally open contacts that only let current flow when activated, normally closed contacts that do the opposite, and output coils that energize the actual machine part. These symbols on a screen are digital representations of physical electrical states. To see how this works in practice, let's look at what happens when an operator needs to safely start up a heavy industrial motor on the factory floor. Mapping a normally open contact to a start button connects straight to the motor's coil. Pushing the button completes the circuit and the motor turns on. But there's a limitation. Releasing the button instantly breaks the circuit, shutting the motor off. An operator cannot stand at a panel holding a button indefinitely. The software requires a mechanical memory, a way to lock in that command. Engineers solve this using a structure called a seal-in circuit. In this motor start-stop example, a second contact is placed parallel to the start button, mapped to the motor's power state. Pressing start closes that parallel contact. The operator can let go, and current bypasses the button, flowing continuously. It seals itself in. To safely stop the machine, a normally closed button is wired into the main line. Hitting it forces the circuit open, breaking the continuous loop and killing the power. By combining simple pathways like these, programmers build the highly complex logic sequences that allow facilities to run continuously and safely. This leaves a lingering question. Why did modern industries settle on a computer language that looks like an electrical drawing? Before computers, factory logic was executed by massive walls of physical, hardwired mechanical relays. If you wanted to change how a machine behaved, you had to manually unscrew and reroute hundreds of wires. When microprocessors arrived to replace those heavy cabinets, the new software interface was explicitly designed to mimic those old physical relay circuits. It was a practical translation. Electricians and maintenance engineers could immediately look at a screen and troubleshoot the software using their existing knowledge of physical wiring. As Section 6 shows, this visual standard was globally adopted. From Siemens to Allen Bradley, major industrial platforms all support this shared logic. PLC programming translates complex digital controls into a highly reliable, universally understood language, ensuring that the technicians on the floor can keep our industries moving.